this lab is to observe and measure the motion of a mass swinging in an arc while oscillating on a string. This motion is analyzed using tracker, and then a computational model is used to predict the object's motion and the plot predicted changes in energy. The goal is to determine if the model system satisfies the energy principle, and to spoil the experiment, the result of the experiment was that the total change in energy of the system remained equal to 0, meaning that the energy principle was satisfied. The fundamental principles for this lab were Newton's second law, which is F net, and then also the energy principle. See below, it's where the change in energy of a system equals dW surroundings plus Q, and then other formulas just used throughout were the velocity update, position update, gravitational force, kinetic energy, spring force, gravitational potential, and spring potential. So going on to our observed model. The video was done using tracker, and the initial conditions had a mass of 0.402 kilograms. Position was negative 0.100 in the x direction and negative 0.644 in the y direction, and 0 in the z direction. L equaled 0.7 meters, and velocity was 0 at the start. These were my calculations. I found the oscillation period, and I also calculated for the relaxed length of the string as seen below. So then on to the right over here is where I have my graphs from tracker. And you can see after the beginning, it came and became, you can see the oscillations in the graph. And a big part of the relaxed length of string was that the F net equaled 0, so the force of gravity did equal the force of the spring. Going on to the coding model. As you can see, the first box over here illustrates like the initial conditions that I had for coding, which again were similar to what I had with the observed model. So mass was the same, original position vector and velocity were the same, force of gravity and the spring constant, and then the relaxed length of the spring was 0.1232. And then starting these next two boxes where you have the actual calculations being done. So on the right over here, we have solving for the gravity using the gravity formula, which is when it's a vector, so it's 0 in the x direction, negative mg in the y direction, and 0 again in the z direction. The F spring calculation and the F net calculation again, which this time was gravity plus spring, which we know will equal out to 0. And then we updated the velocity and the position, and that's how we calculated for the oscillating period. Not the oscillating period, but where it was during the oscillating period. In the comparison and possible errors, the observed model could have error with the time values in the y direction. Tracker is not always most accurate. And then in the computational model, could have had issues with the system not actually being closed, and there could have been other forces that are present and acting on the mass. Is the energy principle satisfied? To satisfy the energy principle, the change in energy must be equal to the work done by the surroundings. Since there is nothing acting on the closed model system, the change in energy must equal 0. In the graph, the change of E, which is the change in total energy of the system, remains constant at 0. This is because the kinetic energy equation is equal but opposite to the total potential energy of the system. And then this was just a comparison of the oscillation periods. So in the x direction, one oscillation period was 1.651 seconds, and in the y direction it was 1.5237 seconds. And then at the bottom you can just see the equations for the spring constant, which came on the x direction came out to be 5.82 newtons per meter, and on the y direction is 6.83 newtons per meter. Thank you for watching, and I hope you have a great day.